Let's talk about the inverse of a function. The inverse of a function exists if the function is one-to-one. This is the whole reason why we studied this property of one-to-one functions in the first place. So if our function is one-to-one, then we can reverse the direction of our arrow diagram, and the result will still be a function. Let's make this idea clearer by looking at an example. In example 10, we're starting off with a function y is equal to f of x. In other words, the input values are going to be the x values. So let's label those on the left. We have -2, -1, 0, 1, and 2. And let's look at our output values. Our output values are going to be -8, -1, 0, 1, and 8 like this. So originally um, in our situation over here, 2 gets mapped to 8. So let's put an arrow that goes like this. -1 maps to -1. 0 maps to 0. 1 maps to 1. And 2 maps to 8. So we had seen this example earlier. What we're going to do now is we're going to reverse the direction of the arrows. So what that means is we are going to maybe erase the tips over here like this. We just want the arrows to go in the other direction. So we're just going to have, instead of the arrows going from left to right, they're going to go from right to left. So now it looks like this. When we look at our new Venn diagram, we can see now that the domain of this new function is going to be on the right side. So this is going to be the domain over here. And the range is going to be on the left side. So let me label that as the range like this. And we're going to see later on that this new function that we create is going to be called y is equal to f inverse of x. So it's almost like we have a -1 exponent, but this is not actually an exponent. This is a symbol used to denote the inverse. More importantly, what we can see now is that this is going to define a function because every single input value has only exactly one output value. And this can be seen by the fact that, -8, -1, 0, 1, and 8, they only have one arrow coming out of each input value. Next, let's look at an example of a situation where we don't have a function. So this example is going to be set up in a similar way. We can have our original function is y is equal to f of x, meaning that the output values are the y values. So let's label our domain again. Our original domain is going to be -2, -1, 0, 1, and 2. And the output values, remember, we don't want to write any duplicates. So the output values are going to be 0, 1, and 4. So how does this function look? Well, we map -2 to 4. So let's put an arrow there. We map -1 to 1. So let's put an arrow there. We're going to map 0 to 0. Let's put another arrow there. We got 1 also going to 1. And then we got 2 also going to 4. So I want to take a moment to point out that right now our function is going from left to right, and every input value that you see has exactly one arrow coming out of it. So that means every input has exactly one output. So this is going to be a function. Now what I want to do is I want to reverse the direction of the arrows. So I'm going to erase all the arrow tips on the right. Okay. And let me just extend these arrows a bit. I want to make it totally obvious what's happening over here. Okay. And now let's put the arrow tips on the left side. So we're reversing the direction to make our function go quote unquote backwards. Okay. So what do we notice now? Well, now our arrows are going from right to left. And what we see is that while 0 only goes to one number, it only has one output, that is, it goes to 0. The value of 1 now has two outputs. 1 goes to -1, but 1 also goes to 1. So this is going to fail to be a function. 4 also has two outputs for a single input. 4 is trying to go to -2, and it's also trying to go to 2. So in both instances, we can see that it fails to have just exactly one output value. So in example 11, this is not a function. When we reverse the direction of the arrows. So I think one of the big takeaways is we need your original function y equal to f of x to be 1-to-1 in order for the inverse function to exist. So let's try to put all of this together and formally define what we mean by a function inverse of a function. So I guess the first thing we want to notice is that we for sure require that our function is 1-to-1. So we're going to highlight that. And let's call the domain of our original function A, and what's called the range of the original function B. So I want to label that in my picture over here. So, this set over here will be A, that's the domain, and this set on the right is going to be B, and F is mapping from A to B like this. And what we're trying to say is that F inverse is going to go in the opposite direction. So F inverse is going to go from B to A, and we label that function F inverse as F to the -1, but that's not an exponent symbol, that's a notation for the inverse. So let me make a note about that. If I write F to the -1 like this is not an exponent, it's a symbol representing the inverse function. So looking at our picture, I think we can see that the domain of F is the same thing as the range of F inverse. Also, what we can see is that the range of F is going to be the domain of F inverse. So they sort of switch roles. And another consequence we could see is we could see that if we compose the two functions, in other words, if you first did F and then you did F inverse, it's as if nothing had happened. So you just get the original thing X back. This is true for every X that's in A. So let me draw a little picture to show the situation. We start off with an x that's in A, and then we map x via f into B. So now that maps to the point f of x like this. And then what we're going to do is we're going to map it all the way back via f inverse, and that's just going to take it back to where it started. So we just end up back at x again. Okay, let's do something very similar. This time, we are going to start with our x in B. So let's put the x over here. And when we map x to the set A via f inverse, the image under the inverse function is going to be f inverse of x like this. But what we can see is when we take x, first do f inverse, and then map it back with f, we end up exactly where we started. In other words, first if you take x, do f inverse, and then do f again, you end up with x again. And this is true for every x in B because we started in B. People sometimes refer to these two properties here as the cancellation properties. Why do I suspect that the word cancellation has two L's? Anyways, this is a math class, not a spelling class. Okay, we are now in a position to formally define the definition of an inverse function. So let f be a one-to-one function with domain A and range B. Then the inverse function, f inverse, has domain B and range A. And it's defined in the following way. If I wanted to say f inverse of y is equal to x, that is the same thing as saying that if I were to take f of x, I would get y. So this double arrow that I put right here, this symbol, this double arrow is called a double implication, and it means if and only if. So that means the arrow goes in two directions. A implies B, but also B implies A. So these two statements are equivalent. That's what if and only if means. Okay. So the final thing we'll talk about in this video is, what's the process of actually finding the inverse function? And it's really just a three-step process. The first thing you want to do is you want to write down your equation with x and y. So you want to write y is equal to f of x. The next thing you want to do is you want to interchange x and y. And then the last thing you're going to do is you're going to solve for y in terms of x. So this is the basics of the inverse function. Take care, everybody.